Okay, let's start our final session today. The first talk will be given by Professor Shengyuan from Singapore University. The title of this talk is 2D spin orbit Dirac point, Hourglass Dirac loop, and Dirac chain. Let's welcome Professor Yang. Thank you.
First, thank the organizers giving me this opportunity to present some of our recent works. The title is about three kinds of topological band crossings, basically topological metals or semi-metals. And this is an overview, basically corresponds to three parts. So first is about the 2D spin orbit Dirac point. Second is about the Hourglass Dirac loop, and last is Hourglass Dirac chain. And in each, for each type, we identify concrete material candidates for its realization. The three actually there's a connection between the three types because they are all originated or dictated by so-called non-symmetric space group symmetry in crystals. So this is a big difference from the previous talks they discussed about topological insulators, which basically requires a band inversion. And if for this kind of objects, actually it does not rely only on the band inversion, as we shall see. And so first of all, it's about the 2D spin orbit Dirac points. So Dirac points actually has been extensively discussed in 2D materials, starting from graphene. This is a famous band structure for graphene, and people are interested in this low energy band structure where the conduction valence band touch at discrete Dirac points. And later on, many other materials are found to host such Dirac points, like this so-called graphene, and some 2D boron allotrope, and also phosphorine, and also phosphorine-like structures. And they all have this kind of two-dimensional Dirac cone. And this, if you discuss about band crossing, we need to identify what's the kind of protection mechanism for this Dirac points. For example, in graphene, there are multiple crystalline symmetry stabilize this point, which means as long as these symmetries are preserved, then this point cannot be destroyed, cannot be gapped. For example, we have inversion symmetry, mirror symmetry, or subband symmetry. Each symmetry independently can protect this Dirac points. Equivalently, if the symmetry holds, actually one can show there is a quantized barrier phase. If you go around this Dirac point in the 2D K space, you calculate the barrier phase to find its positive or negative part. And if the symmetry holds, then this barrier phase must be quantized in unit of pi, which means it cannot open gap. Because if it open gap, this one must change continuously. So it's not possible. For all these discussions, it's in the absence of spin-orbit coupling. So this is for 2D case. Emphasize this for 2D. But what if you have spin-orbit coupling? Because spin-orbit coupling is universal. You cannot just artificially drop it out. So generally, for 2D Dirac points, if you add spin-orbit coupling, it will be destroyed. For example, the famous example, the graphene, actually if you include spin-orbit coupling, as shown by King and Malay, actually it opens a small gap at Dirac points. And in principle, this one, strictly speaking, is a 2D topological insulator. Although this gap is extremely small, like 10 to the power minus 3 MeV. Concerning the physical properties, you can consider it's gapless, but strictly speaking, it's insulator. Then is it possible to have a robust two-dimensional Dirac points? This answer is theoretically answered by Yang and King in this paper. in 2015. They show that if you have a system has some kind of non-symmetric symmetry, actually you can have protected Dirac points that's robust against the spin-off coupling. For this non-symmetric symmetry, just show one simple example. So this is the so-called glide mirror. So this kind of pattern itself does not have a mirror symmetry. But if you do a mirror operation, followed by translation by half of a lattice constant, then the pattern will cover itself. So this is so-called glide mirror. And two other key properties for this kind of Dirac point is they occur at high symmetry points on the Brillouin zone boundary. For example, here, it's not occurring as this gamma point, actually as a boundary of Brillouin zone. And actually, these kind of Dirac points only appear when you include it in SOC, when you include it in spin-off coupling. And actually, it's dictated to be present as these particular points. So it's, in a sense, it's a so-called essential band crossing. And we can term this kind of Dirac point as a spin orbit Dirac point to emphasize actually this one is robust against SOC. So now the challenge is we know the theory. Okay, if we have this kind of symmetry, we can have spin orbit Dirac points. But in reality, how can I find the material to realize this kind of object? This is not trivial, because if you want to have this Dirac point to manifest in any measurable physical properties, you want this point to be close to the Fermi level for the solid states. Only properties near the Fermi level are probed. So here, actually, these kind of Dirac points already appear in several material systems. For example, this is for 2D bismuth, monolayer 2D bismuth. You can see actually there is a Dirac point here. Four-fold degenerate Dirac points. However, this one is far from the Fermi level, so about 0.5 eV. So it's not a good candidate. It's not a good candidate. So if you artificially dope the system, for example, you place some elements to shift the Fermi level down to make it passing through these Dirac points, then usually the structure will be unstable. If I replace some elements, typically the state structure becomes unstable. So here, the challenge is how to find the material. So we actually identify the first example in this monolayer half-near germanium telluride family. This structure is a bit complicated. So this material exists in bulk. It's a bulk layer structure. For example, this shows the 2 layers. And experimentally, actually people already obtained ultra-thin layers, atomically thick layers, by using simple mechanical exfoliation method. Actually, some transport measurement has already been done for this material. We just isolate one of the layer, so-called monolayer, and this is the photon spectrum to show the stability, dynamical stability of the structure. So this one is stable. And most important is the band structure. So this one is the band structure without spin-off coupling. So you can see several features. There are crossings here and here. This is at X point. X point is as a boundary point of the Brillouin zone. And here, this is actually twofold degenerate line. The twofold degenerate line. And there is one point here. 1.12. This crossing between 2 of the bands, and the 2 bands become degenerate along xn. Most importantly, if you include the SOC, then you find the original line, doubly degenerate line, splits. Now each band here is still twofold degenerate because this system has inversion symmetry. Each band is twofold degenerate. And you see that there are bands crossing at X point. This point is fourfold degenerate. So this is indeed Dirac point. If you plot the energy surface, you can see this Dirac cone feature. And we analyze the symmetry of this for these Dirac points. The crystal has one important symmetry is a glide mirror. if you do a mirror operation with respect to the xy plane, and you also shift the crystal by half lattice constant, it will recover itself. And we also have two important symmetries, P and T, inversion and time reversal. Dictated by these three symmetries, we can write down the K dot P Hamiltonian at this point. It looks like this. So this is a 4-band. So sigma and tau are 2x2 point matrix. So this is 4x4. And it describes this Dirac point feature at this x points. And another interesting thing I want to mention is actually this one has a non-trivial Z2 invariance. So you look at this structure. If I just evaluate the Z2 invariance, I find it's actually non-trivial, 2D Z2 invariance. So this is weird because this one is a metal. The formula will pass through here. So this is a metal. So we can define a Z2 for metallic state. But somehow you can also understand it, right? Because here, although it's a metal, as you notice this gap is closed indirectly. So at any k point, you have a finite direct gap, which means you can actually identify a set of bands below the local gap. This forms a closed manifold. So you can define this Z2. And actually, in previous work, we proposed such a kind of fix called the 2D Z2 topological method. So this is in a model study. Basically, the key feature is the bands, the gap are closed indirectly, and the Z2 is non-zero, so you can still have spin helical edge states, just like in 2D topological insulator. And actually here, this material represents the first real example. And indeed, if we calculate the edge spectrum, we can see these helical edge states. They are localized as the central boundaries. And we also, by replacing the elements, I can find some other examples. All these examples actually exist in bulk form, so which means just by exfoliation, you may get 2D spin of Dirac method. So the second one is about the hourglass Dirac loop. So I'm going to start with concrete material. This is actually another layered example. Look at this. So actually, the unit cell contains many atoms. It has a formula units like this. So quite complicated. But this one, unfortunately, exists in nature. Actually, it's layered materials already synthesized. And experimentally, again, few layer structure already obtained by mechanical exfoliation. Some transport, magnetic transport already done on this material. And if we calculate the band structure, this is the band structure with spin-orbit coupling. One key feature you notice here, close to Fermi level, you see this kind of hourglass type dispersion here. So this dispersion occurs on this side surface of the brilliant dome. So actually, if we scan the dispersion in this plane, we find it's actually a loop traced by these crossing points, the neck points of the hourglass. Actually trace out. This point actually trace out a loop on this plane. This is the DFT results. If we calculate the local gap, we can see this loop. This hourglass dispersion has been predicted and identified previously, for example, on the surface of 3D TI, topological insulator, and also in the bulk of this oxide material. Also, this kind of Dirac loop. Here, I emphasize Dirac means it's fourfold degenerate. So here, for our system, the important symmetry that dictates the presence of the Dirac loop is this mirror, glide mirror. So if you do this mirror operation and translate the crystal by half lattice constant, it will recover itself, and also P and T. So because of PT symmetry, each band is doubly degenerate. And most importantly, this PT-related pair, because there are two states here. The two states share the same glide mirror eigenvalue. For example, here, the two bands both have this positive eigenvalue. These two bands have negative eigenvalue. Because of this, because of this Dirac point is protected because the two have different mirror eigenvalue, so they cannot hybridize. And another important observation is by going from one high symmetry point, S point, to a point on the boundary. For example, if we go to X or R, or go to the arbitrary points, then there must be a partner switching between the Cramer's pair. For example, here, the four states degenerate together all have a positive 1 eigenvalue. If you go to here, it must be grouped into two positive, two negative. So in between, there must be a crossing. So actually, this partner switching is the key reason why you must have a Dirac point in between. And since every path has a Dirac point, so this one will trace out a closed Dirac loop on this plane. And the Dirac loop also has protected boundary states, surface bands. So usually people call them the drum heads type of surface bands. Because this is Dirac, so we actually have a pair of drum head surface bands. You can see here, actually two bands. More clearly see here, two bands. And another interesting thing about this material, because it's layered, we can explore its model layer. So previous discussion all about bulk. So now if we go to model layer, for model layer actually we find that there are Dirac lines, nodal lines on the boundary of the brilliant zone, as shown here. This is a nodal line on the boundary. This is without spin-out coupling. If you add spin-out coupling, this nodal line will be split, slightly split. And at the high symmetry point M and Q at the boundary, the two, they are still protected band crossing. So these are the 2D spin-out Dirac points we mentioned before. So but since this splitting is so small, so better this one is still regarded as a nodal line 2D material. So finally, it's about Dirac chain. So what I want to discuss is something like this. So previously you see a loop, a nodal line. That's a loop. Now, if I have two loops touch at one point, like this, then because this brilliant zone is actually extended, case space is extended. So actually you can imagine there is a chain running along this direction. This is a chain. And each loop is a Dirac loop, as I mentioned in the previous section. So each loop is fourfold degenerate. And there are two kinds of loops, orthogonal to each other, touch at one point. So this is what we call a Dirac chain. Okay, so here this is another schematic picture showing dispersion along a path like this. So along a path like this, you have hourglass type of dispersion. And we identify candidate material, which is radium oxides. This important symmetries for this kind of structure is this Fourier symmetry. There are two glide mirrors orthogonal to each other, and also inversion symmetry, and again time reversal. And this material actually exists in chemistry for many years, and used to be some good catalysts. Actually, I found it from literature. So this is a band structure. So it's a metal. So it's actually the bands near the Fermi level dominated by the T2G orbitals from the rhenium. And if you zoom in, you can find this kind of band structure here. Along the different paths, you have this kind of crossing. Actually, these are the crossing correspond to the hourglass, neck point with hourglass. Just like this. So we analyze the symmetry. For example, this is for the front plane. This is brilliant zone, the front surface of the brilliant zone. If you go from this R point to any point on these two lines, then there must be this kind of hourglass dispersion. And therefore, this crossing points will trace out a Dirac loop. And similarly, for the top surface, you do the same argument. You have another loop. And the two loops must touch at a single point on this UR path. And this is the DFT results. If we trace out the crossing points on the front surface, it's like this, and on top surface, it's like this, the two loops. Previously, people discovered the so-called wire chain. Wire chain is the material with without inversion symmetry. So the chain is twofold degenerate. Here we have Dirac. Dirac means fourfold degenerate. Question naturally arises: is the Dirac chain simply two copies of wire chain? Can a Dirac chain simply be divided as two copies of wire chain? Which means if you, for example, if you vary the structure of a wire chain material, if you retain the inversion symmetry, does it automatically gives you a Dirac chain? The answer is actually no. You require more. It's just like the comparison between Dirac point and Y points. Y point is topologically robust, but Dirac point you require additional crystalline symmetry. Otherwise, the two Y points will annihilate. So here, this is the same. Because I mentioned the two crossing bands must have the opposite glide mirror eigenvalues, but there is no guarantee. Each pair, each doublet here must have the same glide mirror eigenvalue. Right? So it's not guaranteed. And indeed, if you look at this side surface, actually this side of the surface also has a glide mirror. So if you simply do the arguments, okay, if I have a glide mirror, then there must, if I have P and have T, there must be a Dirac loop. Then this is wrong. Actually, there is no Dirac loop on the side surface because the doublets actually has opposite glide mirror eigenvalue. So only a single Dirac point is left on this Ty path. So there is no third Dirac loop. And again, if we look at the surface states, we see a pair of Zhang path type surface states. This is 1, this is 2. And here, you can see this surface bands. And on this side surface, since we have Dirac points, so we actually have two Fermi arcs connecting the two Dirac points. Okay, so this is a summary of my talk. I talk about the three objects. One is the 2D spin-orbit Dirac points. We identify actually the first relates to material with this 2D spin-orbit Dirac points close to the Fermi level. And simultaneously, it happens that this material is also the first example for the 2D Z2 topological method. And the second is about these two materials. We find the hourglass Dirac loop in the 3D bulk, and also nodal line and 2D spin-off Dirac point in the modular form. So indeed, there are very rich band features in this kind of material. And the last is we propose the concept of Dirac chain metal, and we find an example for its realization. Okay, and last, I acknowledge my contribution from my collaborators. So Shengyuan, my PhD students, and Chuang is my postdoc. And this Guang-Yu and Lisa visiting students from Beijing Institute of Technology. And Xianlei is a previous postdoc and now at Beihang University. And I have close collaboration with Yu Guiyao from the Beijing Institute of Technology. Okay, thank you.
Thanks for the nice talk. Now welcome questions and comments.
Thank you for the talk. I want to express about the niobium 3 silicon tellurium. Second. And so you mentioned there is a paper in Nature Physics in 2015. So there is some experimental results. So can you explain their experimental results by your calculation? Like, is there any contribution by the hourglass to their transport properties or something? Thank you.
If I remember correctly, they observed some anomalies in the magnetic transport in this kind of material. So usually, even if people see anomaly in magnetic transport, nowadays they try to find is there any topological band crossing in the kind of structure. So I do not have a definite answer for this one because you see this band structure is actually quite complicated, very complicated. So there are many bands crossing. So if we think actually the contribution is beginning from this topological band crossing, then there may be some connection between the two. But so far, I cannot give a definite answer for this one.
Okay, because I see gamma point there are some bands there, so.
Yeah, the theory for magnetic transport is actually quite tricky. It's quite tricky. So I think nowadays we still don't have a like first principle kind of evaluation for magnetic transports. Actually, we are developing some semi-classical theory for explaining the magnetic transports. We think that we are having some results. We show that actually the chiral anomaly is not the only important contribution. Because previously, when people do a measurement on wild-type metal, they see some negative magnetic resistance. They attribute to the chiral anomaly for the wild points. But actually, we show that this is not true. Actually, we find even for gap case, from model calculation, for gap case, we can have negative magnetic resistance in the semi-classical transport regime. So there are additional contributions. We have a theory for this, but I don't know whether it's difficult to implement in DFT calculation. If we can do that, then maybe we can address your question more clearly.
So I have another. So for you mentioned like rhenium oxide, the nano metal. So it's a metal.
Yes. Yes.
So you mentioned there is already have someone do the experiment on it, or?
Not on the transport or other property, because we search the literature, the papers studying this one is quite old, actually.
Okay.
In the 70s or 60s, people do the measurements, and they confirm it's a metal, it's paramagnetic,
Yeah.
and I think they don't have more conclusion on that. So I think we definitely deserve more careful study for this one. But I use this one as a candidate for the new phase, the so-called Dirac chain. But we actually can see the band structure is not so good. It will be great that we can find a better candidate material to realize the hourglass, to make it more close to the Fermi level, and the crossing point to be exactly line on the Fermi level. That would be perfect. So this one is not ideal.
Okay, because I'm just wondering, is there any difference in like property in chain, Dirac chain or wire chain? That's some transport or something property can measure difference.
Yeah. So for I think the property you can derive it from the loop. So some people present theory for the loop. Now we just have two loops.
Yeah.
So one possible feature is that because of the because you have two loops. So if you look at the surface, then the strong head type surface band will appear on this surface and also the front surface. So the features associated with the surface band will appear on two surfaces, but not the third one. So probably that's one feature.
It's a metal, or it's a metal or not a metal?
It's a metal.
So
surface band
property or?
Yeah, surface band will coexist with the bulk bands.
Okay.
But hopefully the surface band will dominate. Okay, that will depend on the material and exact condition and surface.
Okay, I see. Thank you.
Okay, questions and comments? Okay.
Yeah, thank you for your talk. For the first part of your talk, you showed this fourfold degeneracy in this was it hafnium, gadolinium, tellurium. Is there any consequence from this, like some wide boundary correspondence, or what is the consequence of this state?
Yeah, that's a good question. So for the Dirac states, there may be and there may not be boundary states correspond to this kind of Dirac points. So in the original paper by Yang and King, they actually had some discussion on this. So I think it will depend on the particular material. It's not even if there exists the surface band may not be purely due to this Dirac process. There may be some other topological reasons. Yeah, that's.
Okay,
what I
you
see.
didn't see anything here.
I see Dirac bands here, but this one is not actually attributed to the
Comes from the
Dirac point. Yeah, it's actually attributed to the Z2 invariance due to this band inversion at the X points. It's not actually due to the Dirac point.
Thank you.
So this one look like a Rashba band, but it's one-dimensional, isn't it?
This one.
Yeah.
Yeah, it looks like a Rashba band, but I think it's actually I don't know
So how about the spin polarization? Is it perpendicular to the plane or in plane?
So here we didn't check.
But that should be spin polarized. Isn't it?
Yeah, spin polarized. This one.
So I'm wondering whether it's
I don't
perpendicular
think it's,
different or different.
I don't think it has a particular direction here because actually the symmetry is rather low. So I won't expect it has a particular polarization direction.
But you include spin orbit coupling here.
Yes.
Yeah, then it should have some kind of momentum and spin locking. Isn't it?
Yes.
Yeah, so
that's
that
true.
could be interesting.
Yeah. So
But then you have to identify the spin polarization for each band.
Yeah, we
It
can
must
do.
be polarized.
Yeah, it must be polarized. Just I'm not sure whether it's polarized at a fixed direction because it must may rotate as you go along as a
Yeah,
k-path.
but you can use that use WASP to plot it.
So what's so you're asking this question because you're thinking of some spintronics
Yeah,
equation?
yeah, of course.
Yeah, it's possible because for this kind of topological metal, because it's a metal, so we are thinking that probably one advantage is that if you can, because it's metal, so you can probably realize the superconductivity in the bulk more easily. Then people talking about realizing the Majorana fermion on the boundary due to this topological edge states. In the previous proposal, you usually need a nearby superconductor to make a proximity effect, to make this edge state superconducting by proximity effect. But now, if there is a chance to realize superconducting in the bulk, then the proposal may be more easier to realize.
The two bands, each of them is contributed by H atoms on both sides, right?
Yes.
Okay, all right. That's my question.
So here we do a ribbon calculation. So this, if you take a states, actually symmetrical anti-symmetrical combination of states of two edge.
So the Z2 material, I thought it's an edge state to connect to capacitor.
Yes. But here since two are shifted, so we cannot see the clearly here because there's no global gap in the bulk.
Where is the zone boundary?
Okay.
Where is the zone boundary? Point 8 is zone boundary.
Point is not the zone boundary, so we didn't show here. Here it still goes up. The bulk bands still goes up.
So zone boundary is outside this
Yeah,
figure.
outside. It's point.
So these two points goes to the Fermi level or not?
I think they merge into the bands, so we cannot clearly identify the edge states from the bulk. That's the reason why we didn't plot this path.
So it goes to the valence band before the Fermi level, below the Fermi level.
Yes. That's I cannot remember exactly. So what we can see is this two edge states is only clear in this region. Other regions overlap with the bulk band, so it cannot be clearly differentiated.
Thank you. Any more questions or comments? Okay, thanks for the nice talk again.
The next talk will be given by Professor Jithao Zhang.